This is the second part of Chapter 2. We are in Section 2.4, the chain rule. The chain rule is very useful, and before introducing it, we will review a key component of the chain rule, which is composition functions or composite functions. So the first example says let f of x equal 3x minus 2 and g of x equals square root of 4x plus 5. Then find f of g of 3. So for these problems, we always start on the inside, and this is a composition function or a composite function. And so we have this is equal to f of and g of 3. We find by taking the square root of 4x, and instead of x, we're going to put 3 plus 5. And working this out, we have 4 times 3, which is 12, plus 5, which is 17. So now we have to find the square root of 17. So f of square root of 17 is going to be, substituting this into our f function, we have 3 times the square root of 17 minus 2. In part B, you'll notice that the f and the g are reversed and flipped. And so we're going to have g on the outside. So g, and I start always on the inside. And f is 3 times x, and instead of x, we have a 3 this time, minus 2. And so this is going to work out to being g of 9 minus 2 is 7. And so g of 7 is going to be the square root of 4 times 7 plus 5, which is going to work out to being 28 plus 5 is 33, so the square root of 33. The next example says let f of x equal 2x squared plus 1 and g of x equal 3x minus 4. Then find, and if you notice this time we don't have numbers in here, it's left as g of x. So we're going to have f of, and g of x is just going to be this function, which is 3x minus 4. And now we're going to substitute this function into f. So f is going to be 2 times, and instead of x, we're going to put 3x minus 4 squared plus 1. And from here, you can either simplify this, multiply it out, or just leave it. We'll leave it for right now. Likewise, for part B, our inside function is f of x. So we have g of, and f of x is equal to 2x squared plus 1. And now we're going to substitute this into g. So we have 3 times, and instead of x, we're going to put 2x squared plus 1, and then minus 4. From here, you can combine the 3 and a minus 4 when you distribute this, and you'll end up with 6x squared minus 1. The next example says write h of x equals 2x minus 3 squared as a composition function of two functions f and g, such that h of x is equal to f of g of x. So that inside function is our g of x. And the inside function that we have here is 2x minus 3. And our outside function, which we call f of x, and that's going to be what we have left over, which is x to the second. And you can always check this by going backwards to finding h of x. So on the next one, same thing, h of x is equal to 3 square root of 4x minus 5. Write it as a composition function where h of x is equal to f of g of x. So we're going to go ahead and say g of x is equal to our inside function, which this time is inside the radical, which is 4x minus 5. And then our outside function, which is going to be f of x, which is what's left over. We have a 3, and then we have the square root of our x. And again, you can check it working backwards in order to find h of x. The chain rule says to take the derivative of the outside function while leaving the inside function the same, then multiplying by the derivative of the inside. And so this is what we're going to be exploring next. So the chain rule says if f and g are differentiable, then the composite function f of g of x or f of g of x, where you have a function inside another function, is also differentiable. And the derivative of this composite function is going to be the derivative of the outside, keeping the inside the same, times the derivative of the inside. And it's written there in function notation and then also with words. So the next example that we have says to find the derivative dy dx if y is equal to 2 times 3x squared minus 5x all raised to the fourth power. So what we saw before was where we would actually multiply this out. It's a little bit more difficult now to do, especially if the outside exponent wasn't just a 4, but maybe like a 20. So we have our inside function. If you recognize that, that's going to be 3x squared minus 5x. So to find our derivative, we're going to take the derivative of the outside. The outside function is going to be 2 to the x to the fourth, and keep the inside function the same. So we have a 2 times, bringing the exponent out in front would be 4, leave the inside function the same, and then subtracting 1 from that exponent, times the derivative of the inside function, which is what I underlined here, which is going to be 6x minus 5. So just cleaning this up a little bit, again, not much you can do, but we have 8 times 6x minus 5 and times 3x squared minus 5x to the third power. The next one says find the derivative of, and I'm going to go ahead and rewrite our function as 3x squared minus 4x raised to the 1/2 power, just so that way it makes it a little bit easier to take the derivative of. The inside function I will double underline. It's 3x squared minus 4x. So to find dy dx, we take the derivative of the outside, which is x to the 1/2, leave that inside function the same. So it's going to be 1/2, leave the inside function the same. Subtracting 1 from the exponent, we have negative 1/2 times the derivative of the inside function, which is 6x minus 4. So from here, we can clean this up. I'm going to go ahead and factor out a 2 from my last parentheses and move the negative 1/2 part down to the denominator. So we have 2 times 3x minus 2 all over 2 times the square root of 3x squared minus 4x. My 2's are going to simplify. And we have 3x minus 2 all over the square root of 3x squared minus 4x. The next example says to find the derivative if f of x equals negative 2 divided by 3x squared minus 4x plus 5 all raised to the third power. So first thing I'm going to do is rewrite this as negative 2 and then 3x squared minus 4x plus 5 raised to the negative third power. Taking the derivative of this, I have my inside function, which is inside the parentheses, and I'll double underline. And I have negative 2 times negative 3 times 3x squared, keeping that inside the same. Subtracting 1 from our exponent, we get negative 4. And then times the derivative of the inside, which is going to be 6x minus 4. From here, we can clean this up. And we have negative 2 times negative 3, which is 6. And then I have a 6x minus 4 divided by, and then since that parenthesis in the middle is negative exponent, I'm going to go ahead and move that to the denominator. So we have 3x squared minus 4x plus 5 raised to the fourth power. You can also factor out an additional 2 in the numerator and rewrite this as 12 times parentheses 3x minus 2, and that's an equivalent answer. The next example, we're going to go ahead and circle, and we will work on that one together in class. The next example says the cost of producing X units of a particular commodity is C of X equals 1/3 X squared plus 4X plus $53, and the production level, T hours, into a particular production runs is X of T equals 0.2 T squared plus 0.03 T units. At what rate is cost changing with respect to time after 4 hours? So if you notice, the commodity is with respect to x units. And then we also have x with respect to t, which is our time in hours. And they're asking for a rate, which we know is a derivative, of costs changing with respect to time. So they want us to find dc with respect to time, so dt. So in order to do this, I don't have a function that is c in terms of t. So you could rewrite this. Another way to do this is think of it as the derivative of c with respect to x times the derivative of x with respect to t. And this is, if you were to cancel out those d of x's, you would be ending up with dc over dt, which is exactly what we have. And so the derivative of c, which is up here, with respect to x is going to be 2/3 x plus 4 times the derivative of x with respect to t. We're going to have 0.4 t plus 0.03. And it wants us to know what this would be after 4 hours. So I need to evaluate this after 4 hours, which would mean t is equal to 4. But if you look at your formula here, we actually have x's. And the x value that we have, we don't yet know. So I need to figure out what x would be when t is 4. So in order to find x of 4, I'm going to substitute this in to my formula. I have 0.2 times 4 squared plus 0.03 times 4, which works out to being 3.32 units. So I'm going to go ahead and put that down over here. From here, I'm going to substitute in x is 3.32 and t is equal to 4. And when we do that, we are going to arrive at a value of 10.1277. And so what this says is after 4 hours, cost is going to increase. So increases at a rate of, and we're going to go ahead and round that 2 decimal places. So we'll say $10.13 per hour. And so if you look at this, your answer is DC, which is our cost, and DT, which in this problem is in hours. So it's a rate, and so it's in dollars per hour. The next example says, Liz manages an appliance manufacturing firm. She determines that when blenders are priced at P dollars a piece, the number sold each month will be D of P equals 8,000 divided by P. Furthermore, she estimates that T months from now, blenders will be selling at a price of P of T equals 0.06 T to the 3/2 plus $22.5 a piece. At what rate should Liz expect the monthly demand DP to be changing with respect to time 25 months from now? Will the demand be increasing or decreasing at this time? So the first one is finding the monthly demand DOP to be changing with respect to time. So we're asking to find D of our demand with respect to time. And again, looking at our functions, we have D of P, so I'm going to rewrite as 8,000 P to the negative 1. And then we have our P of T function with our price. And so we can think of this as D with our demand with respect to price, dP, times dP, dt, the price with respect to time. So going ahead and taking the derivative of our demand with respect to price, we end up with negative 8,000 p to the negative second times taking the derivative of the price with respect to time. We get 0.09 t to the 1/2. And this does say 25 months from now. So we're going to evaluate this when t is equal to 25. And if you notice in our function, we also have price. So I need to find out the price when it's been 25 months. And so in order to find our p-value, going to go ahead and substitute in t is equal to 25. And we have 0.06 times 25 to the 3 over 2 plus 22.5, which works out to being $30. So P is going to be 30. And then substituting those both in to our formula here for d sub d of dt, we get -4. And so what this means is that 25 months from now, the demand for blenders will be decreasing since it's negative by 4 units per month. So, and again, looking at our units that we have, demand is in blenders, and our time that we're talking about here is in months. So it's decreasing also because it is negative. The next section that we have is 2.5, which is a marginal analysis and approximations using increments. Marginal cost is if C of X is the total cost of producing X units of a commodity, then the marginal cost of producing X naught units is the derivative C prime evaluated at X naught. For X naught sufficiently large, the marginal cost C prime can be used to estimate the additional cost of one additional unit when occurred when the level of production increases from X naught plus 1 to X naught. Similarly, the same holds true for marginal revenue and marginal profit. So the next example that we have says a manufacturer estimates that when X units of a particular commodity are produced, the total cost will be C of X equals 1/8 X squared plus 3X plus $98, and furthermore, that all X units will be sold when the price is equal to 1/3 times 75 minus X dollars per unit. Find the marginal cost and the marginal revenue. So in order to find our marginal cost, we need to find C prime of X. And we have our C of X function there, our cost function, our total cost. So I just would have to take the derivative of this. And so taking the derivative, we have 1/8 times 2X plus 3, which would simplify to 1/4 X plus 3. And that would be our marginal cost function. And we also need to find our marginal revenue. And if you look, we do not have a revenue function. So in order to come up with our revenue function, we need to multiply X, the number of units, times that price. And so we have that. And we have X times our price at which they will be sold, which is going to be 1/3 times 75 minus X. Distributing this through, we will have 25X minus 1/3 X squared. And we need the marginal revenue. So in order to find that, I need to take a derivative of this. And we get 25 minus 2/3 X to the first power. And so we have our marginal revenue. And up here we have our marginal cost. Part B says use marginal cost to estimate the cost of producing the 37th unit. What is the actual cost of producing the 37th unit? And so we have to look at the change in cost of producing 36 to 37th unit. And we can do this, and it can be estimated by finding the marginal cost of the 36th unit. And so we have C prime of 36 is going to be 1/4 times x, which is 36, plus 3, which works out to be 12. So our marginal cost of producing that 37th unit is going to be $12. The actual cost, in order to find our actual cost, we are going to have to do C of 37 minus C of 36. And so using your cost function that was given to us up at the very beginning, we're going to plug in 37, and when we do, we get 380.125 minus plugging in 36 into our cost function and evaluating that, we get 368. When you subtract those, rounding it 2 decimal places, we get $12.13. So they're relatively close to one another. The problem continues on to the next page, and part C says to use marginal revenue to estimate the revenue derived from the sale of the 37th unit. What is the actual revenue derived from the sale of the 37th unit? So likewise, for revenue, we're going to have to use the marginal revenue, so R prime of 36, in order to estimate the revenue derived from the sale of the 37th unit. And so we have 25 minus 2/3 times 36, which is going to be $1. And the actual is going to be R of 37 minus R of 36. And then substituting in 37 into our revenue function, we are going to end up with 468.67 minus, and then substituting in 36 into our revenue function, we get 468. So this works out to being about 67 cents. So again, relatively close to one another. The next example that we have says Quentin is a business manager for a company that manufactures digital cameras. He determines that when X hundred cameras, our units are going to be X hundred cameras, are produced, the total profit will be P $1,000, where P of X is equal to, and you have a function there, Quentin plans to use the marginal profit to make a decision regarding future productions. So the first question says, what is the marginal profit function? So in order to get this, we have to take the derivative of our profit function. So we have P prime of X, which is going to be negative 0.0105 X squared plus 0.14X plus 25. Part B says the current level of production is X equals 10 or 1,000 cameras, because that was our units. Based on the marginal profit at this level of production, should Quentin recommend increasing or decreasing production to increase profits? So profits, our marginal profit at 10 is equal to 25.35. So our marginal profit for 1,000 cameras would be 25.35. And so it's going to be a 1 unit increase will increase profit, and the reason why it increases is because that value is positive by about, and our units are 25.35, and we are in thousands of dollars. And so since this is positive and we do have an increase in profit, this means that we want to increase production. Part C says the current level of production is 80 or 8,000 cameras. Based on the marginal profit at this level of production, should Quentin recommend increasing or decreasing productions to increase profit? So in order to figure this out, we're going to do exactly the same thing. So taking the derivative of our profit function for our marginal profit and substituting in 80, we get negative 31. And so this means that a 1 unit increase will decrease, and again that's because it's negative, so we'll decrease profit by about $31,000. And since this is a negative value and we are decreasing our profit, this means that we would want to decrease our production. The next section that we have is 2.6, which is implicit differentiation and related rates. This is a challenging section, and definitely the more practice that you have, the better off you will be. So first thing is, remember that d dx is an operator that instructs you to take the derivative and treat x as the variable, whereas d dy is an operator that instructs you to take the derivative and treat, this time it's y, as the variable. So the first example that we have says find the following. So taking the derivative of 3y squared with respect to y is nothing new. This is exactly what we've done before. You would end up with 6y. Likewise, b says to take the derivative of 3x squared, this time with respect to x. Well, that's my variable that I have there. Just like before, it was a y and I was taking it with respect to y. This time my variable is an x and I'm taking my derivative with respect to x, and so it's just going to be 6x. Those are nothing new. That's exactly what we've been dealing with so far this chapter. The next one though, however, has taking the derivative with this with respect to x, and if you notice your function this time has a y in it, not an x. And so we do this kind of like by using the chain rule, but we also don't know what y is, and we don't know if y is a function of x itself. So in order to find the derivative of this, we're going to go ahead and take the derivative, keeping that y variable the same. And so we end up with 6y times, and then I have to take the derivative of that inside function, or my variable, with respect to x, so times dy dx. So a little different here. The next one's the same thing. It's asking us to take the derivative with respect to y, but our function is now 3x squared. And so going ahead and doing that, you'll notice that those variable and the operator that you're asking to take the derivative with respect to is not the same. And so we're going to have 6x times the derivative of x with respect to y. The next definition that we have is an explicit function, and on the next page is an implicit function. An explicit function is a function in which the dependent variable can be written explicitly in terms of the independent variable. For example, y equals f of x. So we can isolate y by itself. And for example, we have y equals 3x squared minus 2x plus 1 is an example of an explicit function. Those are the types of problems that we were able to take derivatives of so far. They are easy. You just use your power rule, your chain rule, your product rule, your quotient rule, and you can take the derivative of that. On the next page, we have implicit function or relation. This is a function or relation in which the dependent variable is not isolated on one side of the equation. For example, the equation x squared plus y squared equals 1 represents an implicit relation, and this is specifically a circle. I do want to point out that you could technically solve this for y and make it an explicit function. However, we are trying to expand upon taking derivatives of more complicated functions, which often arise in business and other areas. So the first example that we have says, given 2x squared plus y squared equals 4, find the derivative dy dx. So if you notice, this is an example of an implicit equation, and if we were to go ahead and take a derivative of this with respect to x, the first term we have is 2x squared, nothing new. We just go ahead and take the derivative of this like normal. But if you notice the next one, I'm asking you to take the derivative with respect to x, and it has a y in there. So we're going to go ahead and take the derivative of this, leaving the y the same. So we have 2y, but I also have to consider that y could be a function of x. So times dy dx equals, and whatever you do the left side of the equation, you also have to do the right side of the equation. So I was taking the derivative of this with respect to x. So the derivative of 4 with respect to x is just 0. And so I was asked to find dy dx, and I have it in my answer down here. However, it is not yet isolated, so I need to isolate that. So I'm going to subtract 4x on both sides, and I have 2y times dy dx equals negative 4x. And then the next thing I'm going to do is divide both sides by 2y. And when I do that, we have dy dx is equal to negative 2x all over y. And here is my formula for my derivative of my implicit function. And I want you guys to note at the bottom that we can solve this implicit equation for y to arrive at two explicit functions if you were to isolate y from the beginning. The top and the bottom of the unit circle respectively. However, some equations cannot be easily written as one or more explicit function. Thus we need to use the methods of implicit differentiation. So if you notice, if you were to take the derivative of this explicitly, you would arrive at the same answer, and it's typed out there for you. The next example that we have says let the equation of the function be x squared plus xy plus y squared equals 3. Find all points on the graph of the equation x squared plus xy plus y squared equals 3 that has horizontal tangents. So horizontal tangents we've seen before, and this is where the derivative is equal to 0. So I'm going to rewrite this as dy dx would be equal to 0. So we would have to take the derivative of our function, and notice that we have to use implicit differentiation. And so taking the derivative with this with respect to x, we're going to have 2x plus, and now if you notice we have two different things being multiplied together here that are not the same, two different variables, and we're going to have to use the product rule. So we have the first one times the derivative of y is just 1, but we have to consider dy dx plus the second times the derivative of the first, and the derivative of x with respect to x is just 1, plus the derivative of y squared with respect to x is going to become 2y times, again, dy dx equals, and the derivative of 3 with respect to x is just 0. From here, we need to get our dy dx's isolated. So I have some terms that do not have a dy dx. I'm going to go ahead and subtract those over to the other side. And I have x times dy dx plus 2y times dy dx equals, and then subtracting everything else to the other side, minus 2x minus y. From here I can factor out a dy dx, and I have x plus 2y equals negative 2x minus y. And so dy dx is going to be equal to negative 2x minus y all over x plus 2y. And so that is our derivative function. From here, though, we need to be able to figure out where this is equal to 0, which is what we had up here, where the horizontal is tangent. And so we have, setting this equal to 0, we are going to have multiplying the denominator to both sides. We have negative 2x minus y is equal to 0, or we would have that y is equal to negative 2x. From here, we need to go ahead and figure out what points we would have, which is what it was asking for, find all the points. And so in order to do that, I'm going to substitute in y is equal to negative 2x into my equation. And so I have x squared plus x times negative 2x plus negative 2x squared equals 3. Going ahead and simplifying this, we have x squared minus 2x squared plus 4x squared equals 3. And combining our like terms, we have 3x squared equals 3, or x squared equals 1, or x equals plus or minus 1 when you take the square root on both sides. And so we have two x values. We have 1 and we have negative 1. We need to find our y values by substituting both of these in for our function. So we have to find f of 1 and f of negative 1. And in order to do that, we need to find our y value. We have a formula up above, which is y is equal to negative 2x. So the two values that we have are going to be 1 comma negative 2 and negative 1 comma 2. Part B says find the equation of the tangent line through the point 1, 1. And so that's going to be our x1 value and our y1 value. And our slope, which is equal to the derivative dy dx, evaluated at that point, which is going to be at 1 comma 1. And so our derivative is negative 2x minus y over x plus 2y, evaluated at 1 comma 1. And substituting that in, we have negative 2 times 1 minus 1 over 1 plus 2 times 1, which simplifies to be negative 1, which is our slope. So our equation is going to be y minus y1, which is 1, equals m, or our slope, which is negative 1, times x minus x1, which is also 1. And let's go ahead and rewrite it in slope-intercept form. So we have y minus 1 equals negative x plus 1. And then solving for y, we get negative x plus 2. And so that's the equation of the tangent line that passes through the point 1, 1. The next example, we're going to go ahead and circle, and we will work on that one together in class. When blowing up a balloon, both the volume and the radius of the balloon are increasing, and the rates of increase are related to each other. It is much easier to measure the rate of increase of the volume than it is to measure the rate of increase of the radius. In this section, we introduce the idea of related rate problems, which involve computing the rate of change of one quantity in terms of the rate of change of another quantity, which may be more easily measured. Note, remember that rates of changes are also derivatives. So we have some steps here to kind of go through. Strategies for solving related rate problems. First, read the problem carefully at least twice. 2, assign variables to all quantities that are changing and label all constants in the equation. Step 3, write the givens and the wants in mathematical notation. These will likely be rates of the forms dh dt, dp dt, dc dt, dy dt, etc. at a particular moment in time, and or constants like x, q, or p. I want you guys to notice that all of those derivatives or rates are with respect to time. Step 4 says write a general primary equation that relates the constraints and the variables in the problem. In some cases this is given, and other times you might have to use some geometry or different kind of functions that you have to kind of interpret. 5 says if any quantity in the equation is a constant, you may replace the variable with a numerical value. If any quantity in the equation changes throughout the problem, leave it as a variable. Step 6 says use the chain rule and implicit differentiation to differentiate both sides of the equation with respect to time. 7 says to substitute in the given data and solve for the unknown quantity or rate desired. And 8 says to include appropriate units and make sure your answer makes sense. So this is definitely a challenging section. These are word problems. Again, read the problem twice before even starting. So the first example that we have says the manager of a company determines that when Q 100 units of a particular commodity are produced, the total cost of production is C $1,000, where C squared minus 3Q cubed equals 4,275. When 1,500 units are being produced, the level of production is increasing at the rate of 20 units per week. What is the total cost at this time, and what rate is it changing? So we're going to go through and look at what we do know and what we're looking for. So we do know that the level of production is increasing at a rate of 20 units per week. But we need to be careful with this. This is 20 units per week, and this is a rate, which is a derivative. However, you need to be careful because 20 units is actually going to be, since we're dealing with hundreds of units, is going to be 0.20 hundred units. Likewise, it says when 1,500 units are being produced. So it's again in hundreds of units, so this would be 1,500 units. And so we know that the rate is 20 units per week, and that's the level of production is increasing at this rate. And so we know that dq dt is equal to 0.20. And again, 100 units per week is our time. And it's asking for us to find, so we'll write 100 units per week. And it's asking for us to find what is the total cost at this time and what is the rate that it is changing. So it wants us to find dc dt when Q is equal to 1,500 units. So 1,500 units. And we also know that when Q is at 1,500 units, C we can find in addition. So C squared plus 3 times 15 cubed equals 4,275. Solving this, you would arrive at C is equal to 120, and this is $1,000. So C is equal to $120,000. Again, be careful to make sure you look at those units. And so to find our rates, we have a formula that they gave us. They gave us C squared minus 3Q squared equals 4,275. And what we do is we're going to take the derivative of our function with respect to time. So we have 2C times dc dt minus 6Q times dq dt, and the derivative of a constant is just 0. What do we know? We know that dq dt is equal to 0.2. We also know that q is equal to 15 and c is equal to 120, and dc dt is what we're actually looking for. So we have 2 times 120, dc dt is what we are looking for, that rate, minus 6 times 15 times dq dt, which is 0.2. And this is equal to 0. Going ahead and solving this, we have 2 times 120, which is going to be 240, dc dt, minus, multiplying this out, we get 405 is equal to 0. From here, we get dc dt is equal to 1.6875. And then our units, dc is our cost, and this is in thousands of dollars per, and our time is in weeks. So thousands of dollars per week. So at this level of production, total cost is increasing at $1,687.50 per week. This is multiplying that 1.6875 times 1,000, and you get $1,687.5 per week. So we have another example that we will go through together in class, but these are definitely challenging, and the more practice that you have with these, the better off you will be for the exam.